Thank you for the introduction. My name is Tanya, and this is a joint work with Mark Silberstein and Pavel Lifshits from Technion. GPUs have come a long way from fixed function accelerators to fully programmable high-performance processors that support demand paging. Yet their integration with the host OS is still quite limited. In particular, GPU memory, which can today be as large as 32 gigabytes, has been traditionally managed entirely by the GPU driver without any host OS control. Now, one crucial implication of such design is the OS cannot provide core system services to GPU kernels, such as memory mapped files or efficient file sharing between the CPU and the GPU. Nor can it utilize the additional memory in its disposal for optimizing CPU I/O or support seamless peer-to-peer between the GPU and the disk. But you might ask yourself, why are you telling us about this? I mean, why do we even need these functionalities? Let's take a look at an example and decide together, shall we? So this needs no introduction. I'm sure everyone uses road navigation. Well, at least I do. But let's think how it's implemented, and we'll focus on the server side of it, because this is where the interesting stuff happens. So you want to get from the airport to our hotel. We can look at a map as a weighted graph, with weights being the travel times on the roads. And we have a planning service taking this graph as an input and calculating the shortest path for us to travel on. And in parallel, we have the traffic updater service periodically updating the travel times on the roads. And as a result of the update, we have to reactivate our planning service, and our optimal path may change. Now, how would we implement this? So our map is saved in the file, and we will take two CPU processes, each of them m-mapping the file. So the code is pretty simple. Our updater service just m-maps the file and uses it as if it was a regular memory access. And same for our planning service. We just m-map the file and pass the pointer to the route calculation routine. But what if we now wanted to speed up the planning service by offloading it to GPU? Unfortunately, we can't no longer just m-map the file. We have to read the whole file into the CPU memory and then copy it to GPU. And know that we have to repeat these two steps before each kernel activation, regardless of the fact that perhaps not even the whole file is required by the planning service. But let's take a look at a broader example of some CPU applications sharing file with multiple GPUs. And each of them is working on a different portion of the file. But which portion of is calculation dependent. So our CPU application just m-maps the file as before. But for the GPU, we would have to copy the whole file into each of the GPU memories. So the conclusion is that without OS management of GPU memory, we can't have data-dependent GPU access to files. Nor can we efficiently share files between the CPU and the GPU. And as a result, we have to repeatedly copy the whole file into each of the GPU memories, which is not just tiring, but also pretty inefficient, right? So in order to overcome this limitation, an architectural change is required. We need a tighter integration between the GPU memory and the host OS. And from this understanding came GAIA, a distributed, weakly consistent page cache for heterogeneous systems. With GAIA, we enable memory-mapped files for GPU kernels. We support efficient file sharing between the CPU and the GPU. And we enable CPU and GPU I/O optimizations that were just not possible in the current system design. It turned out we had some really interesting challenges ahead of us. We had to decide the consistency model suitable for the new system, and we had to understand how it will all integrate both with the GPU driver and with the host OS. But today I will talk only about the consistency model we chose, and you are welcome to read the paper for more details. So let's take a look at our system with the unified page cache. What we actually created is a distributed shared memory in which the same file data can now reside in both the CPU and the GPU memory. And not only that, now both the CPU and the GPU can update the file in parallel. So what do we do about consistency? For example, if the CPU updates the file, when will the GPU become aware of the change? Let's start by focusing on the GPU side of the system and talk a bit about unified memory in NVIDIA GPUs. So in the recent GPUs, NVIDIA enabled the same pointer to be accessed by both CPU and the GPU, And they implement it by utilizing the page fault mechanism to trigger the data migration between the two memories. But now if the CPU and the GPU can access the same pointer, NVIDIA also had to address the consistency question, right? And the consistency model NVIDIA chose is the one of strict coherence in 64K granularity, which is one GPU page. According to this model, the same page can be mapped by only one processor at any given moment. So for example, if the page now resides in CPU memory and the GPU requires it, the GPU will trigger a page fault, which will result in the page being migrated to GPU memory. And if the CPU needs the page next, it will also raise the page fault, and the page will be migrated back to CPU. So as you can see, if the CPU and the GPU are write-sharing the page, it results in a constant ping-pong of it between the two memories. But what if the CPU and the GPU are actually fault-sharing the page? For example, the CPU writes to the lower 32K, and the GPU writes to the upper 32K. In theory, they could have worked in parallel, right, if not for the strict coherency limitations. Fault sharing is actually a known issue with UVM, and the official advice from NVIDIA in such cases is to avoid them by having the two processors work each on a private buffer and to merge the output at the end. So we did a small test to evaluate how fault sharing affects performance. We had two GPUs write-sharing a 64K buffer. And we compared this to the official advice from NVIDIA, in which the two GPUs were each working on a private copy of the buffer, and we merged the result at the end. So what we did is we varied the number of loop iterations performed by each GPU, and by doing so, we actually varied the number of page migrations. And this is what you can see on the x-axis. Y-axis is times the slowdown compared to our baseline, in which the two GPUs are each working on a private buffer. So we can easily see that the slowdown due to fault sharing increases linearly with the number of page migrations, which is pretty expected, right? But the slowdown is not the only side effect of fault sharing. It turned out that the fault sharing affects the system as a whole. We did another test where we took a CPU-only benchmark called k-means. It comes from the Phoenix test suite. And we limited it to run on 4 of our system cores. In parallel to it, we ran our fault sharing benchmark, and we allocated the remaining 2 cores for GPU management, which is a common practice with GPU-accelerated workloads. So we ran 2 tests. In the first test, we just ran our k-means on the 4 cores we allocated for it, and we measured its runtime. Of course, it's constant, right? What we did next is we ran our fault sharing in parallel to k-means. Now, what we expected to see is that k-mean runtime will remain constant as well, right? Because it's running on different cores. But to our surprise, this was not the case, and performance isolation was affected due to fault sharing. So this brought us to a conclusion that a different consistency model is required. And the one we chose is the one of laser release consistency. In the paper, we discussed several alternatives, which I won't go over today. So laser release consistency defines two consistency operations called acquire and release. And the general rule is that modifications to shared object will become visible only after the writer releases and the reader acquires. So let's take a look at an example of 2 writers sharing the same file. They both acquire. The first writer writes something to offset 10, and in parallel to it, the second writer also acquires and writes something to offset 20. Next, they both release. And by releasing, they actually notify the other that the file changed. So the next time the first writer, for example, tries to access the file, it will issue an acquire, which will result in the data being propagated from the second writer and merged with the local changes. Now, you might have already noticed a small issue with this protocol if one of the writers is a CPU, because we are now actually forcing the CPU to issue some consistency operations before each access to files, right? And this is, of course, a no-go. So we have to somehow make our synchronization operations transparent to CPU applications to keep them unaware of the weakly consistent page cache. And we do this by limiting the consistency control to the CPU code that invokes GPU kernels. Now, how do we do that? The idea here lies in the understanding of what do we want to happen on the acquire and release sequence. And the purpose of the acquire and release is basically to make sure that the next reader knows from where to get the latest version of the data from. So keeping that in mind, we can play with when the acquire of the CPU occurs and move it back to when the GPU releases. And a similar trick can be applied to CPU release by moving it to when the GPU acquires. And this way, we made the synchronization operations comparatively transparent to CPU processes. Now let's put it all together and look how our code will look with road navigation will look with GAIA. We can now just mmap the file and pass the pointer to the GPU kernel. And that's it. All the synchronization, disk access, the copy to between the memories is done transparently for us by the operating system. We have several more interesting features that enable us to improve CPU and GPU I/O in the paper, as well as implementation details we didn't go over today. And this brings us to evaluation. In the paper, you will find detailed analysis of overheads added by GAIA, as well as benchmark results, including closed source libraries like kublas. And today, we will go over 2 of the 3 real-life applications we used. So the first one is microscopy image stitching. When you take a picture with a microscope, you get a mosaic of small images overlapping with each other, and you need to post-process those images in order to get the original shot. Now, this post-processing was efficiently implemented by the help of GPUs, and we enhanced this process even further by having the CPU work in parallel on half of the output image. So we compare 3 different implementations. In the first one, we have the CPU and the GPU, each working on a private buffer, and we merge the result at the end. And the next, we implement this with UVM in unified virtual memory, in which the CPU and the GPU write-share the output buffer. And as we saw earlier, in this case, they experience fault sharing, which results in 31% performance degradation compared to our previous implementation. And last, we implemented with GAIA, in which we just mmap the file, and the CPU and GPU work in parallel. As you can see, with GAIA, we were able to completely eliminate the fault sharing effect without having to merge the output file at the end. And we'll, of course, conclude with our road navigation service that's been following us throughout this whole talk. We implemented it using Gunrock, which is an open source library for graph processing, and it implements the shortest path application. We had 2 processes, one of them calculating the shortest path on the GPU, and the other was a legacy CPU process periodically updating the weights on the graph. And we had the 2 processes interleaved. And we compared 3 different implementations. The first one is CUDA, in which before each kernel activation, we had to read the whole file and copy it to GPU memory. The second one is UVM, in which before each kernel activation, we had to read the whole file, but the copy to GPU was done transparently for us. And the last one is GAIA, in which we just mmap the file and made sure to acquire and release before kernel activation. So we varied the portion of the file changed by our legacy CPU process, and this is what you see on the x-axis. And y is the test duration. As expected, both UVM and CUDA implementations are not affected by the portion of the file changed, because prior to each activation, we still have to read the whole file. But with GAIA, we were able to get up to 8 times speedup, because the unchanged pages remained cached in GPU memory. To conclude, we extended the OS page cache into GPU memory by implementing lazy release consistency model and eliminating fault sharing effect. We added support for memory mapped files for GPUs, and all of our changes remain transparent to legacy CPU processes and compatible with unmodified GPU kernels. And last but not least, although unfortunately we had no time showing that, we were able to improve I/O performance for CPU legacy processes by caching data in GPU memory. So all of our code is open source, and you can find it online. Thank you for listening, and I'll be happy to take your questions now.
So let me ask you a question. So imagine the hardware architects decide to come up with a new set of primitives and provide coherence between CPU and GPU. And obviously this is coming, if not already there. How will it change your work?
Well, actually, the idea of the unified page cache still remains valid, but I agree that the lazy release consistency model won't be required because, as you said, coherency will be handled by the hardware. But the thing is, this work is, we aimed it for providing a solution for discrete GPUs in x86 systems. And we don't see the hardware coherency becoming available anytime soon in these systems while GAIA is.
Thank you. Let's thank the speaker again.
Thank you.